Hello everyone, we are doing our, what am I doing? Our quick tutorial, and this time we're doing our single sample t-tests. So this is the example we went over in class. A new sheriff promises to reduce response times as part of their election campaign. Population 1 then is the response time under the new sheriff. Right now, he's a new sheriff, so we don't have a lot of information on their overall response time. So we just have the 10 calls that have come in, these first 10 response times, and that's our sample. Population 2 is the response time under the old sheriff. Because that sheriff is no longer sheriff anymore, we have all of the response times over the sheriff's tenure, and we know that that value of the mean of population 2 is 30 minutes. We don't know the variance of this population. So we just collected information about the mean. We don't have the variance. And so in this situation, we're going to have to do a single sample t-test because we do know a parameter about the mean of the population, but we don't know a parameter about the variance. The new response times are listed here. And we have a mean of 28 for those new times. So just looking at this, we can see a mean of 28 is different than a mean of 30. But what a t-test is doing is saying, is it different enough, right? Is it different enough to say something else is going on? Is this an extreme enough difference that it's very unlikely that we would get this by chance? So in step 1, we're going to state our research hypothesis. Our research hypothesis is response times of the new sheriff is less than that of the old sheriff. Notice we have both the populations, kind of response time of the new sheriff, response time of the old sheriff. We're talking about what we're measuring, which is response time here. And it's a directional hypothesis, right? We said that we're going to reduce response time, so we have that less than. Our mathematical research hypothesis will be the same. We have less than in our research hypothesis. We're going to have less than in our mathematical expression of it. So again, it really is pretty formulaic how we can compose these research hypotheses and compose these null hypotheses. Our null hypothesis is that response time of the new sheriff is the same of that of the old sheriff. And so we're going to just say that those two populations are equal to each other. We are testing against this idea of there being no difference between these two populations, right? This is assuming our null hypothesis is true. This is null hypothesis testing. So we're going to take, our assumption is that this will be 0, but we know it's not, right? We've already seen that there's a difference between those two means. So the question is it different enough, right? And first, we're going to need to estimate that standard deviation of distribution of means by estimating the variance of population 2. Again, this is our standard error for our distribution of means. So we had those sheriff response times here. For the new sheriff, we have a sum of 280 for those 10 scores and a mean of 28. To calculate that sum of square, I will just take 26 minus 28. That will give me -2. 30 minus 28 will give me 2. 28 minus 28 will give me 0. 29 minus 28 will give me 1. 25 minus 28 will give me -3. 28 minus 28 is 0. 32 minus 28 is 4. 35 minus 28 is 7. 24 minus 28 is -4, and 23 minus 28 is -5. We're going to square all of those values because if we just added them together there, we would get 0, right? So this is why this is called the sum of squares. We are going to sum up those squared deviation scores. And so when we add all of those squared values together, we get a sum of 124. We are going to estimate the variance almost in every single test that we do from here on out. So if you are not comfortable with this step, please come to either my office hours, your TA's on office hours, your undergraduate teaching interns on office hours, or if we have access to supplemental instruction, those as well, so that we can get really comfortable with this sum of squares because we're going to be using it again and again. Our next step in estimating that variance is we're going to take that sum of squares and we're going to divide it by the number, our degrees of freedom. So we had sum of squares 124. We had 10 people in our sample. That will give us a degrees of freedom of 9. If I had to pick one formula that we talk about so much that I would tattoo it on my forehead, it would be this formula, sums of squared divided by degrees of freedom, because we're going to use this in a number of different permutations kind of from here on out. So we'll take that 124, we'll divide it by 9. We get 13.78 as our estimation of the population variance. Again, this is sample variance, but this is how we're estimating the population variance. Next, there's a number of different ways that we could do it to get that standard error. I'm just going to go ahead and get the estimated variance of a distribution of means. So I'm going to take that sample variance that we just calculated, that 13.78, and divide it by our 10, which is our sample size, and we get 1.378. Our next step is going to be to take the standard deviation, to take the square root of that, because we're trying to get that standard deviation. We're trying to get that estimated standard error. So we're going to take the square root of that value that we just calculated, 1.378, and that will give us 1.17. So this is that piece of the puzzle that we needed in step 2, our estimated standard error of the distribution of means. And so we're done with step 2. If you didn't do this in step 2 and you do it in a later step, that's okay too. But just know that regardless of whether you're doing it in step 2 or in preparation for calculating your sample statistic in step 4, it has to be done. And so it has to be done first, right? So getting it done in step 2 is a good way to just remember kind of what we're comparing it to and what that distribution looks like. In step 3, we're going to use our t-tables. Remember, our t-tables are going to be different than our z-tables because there's not just one t-distribution, there's a whole bunch of t-distributions. And the different t-distributions really depend on how many degrees of freedom there are. So the shape of that particular distribution is set by its degrees of freedom. If you look at the table that I gave you on your formula sheet, if you look all the way at the bottom, it has infinity listed as degrees of freedom, and then you're starting to see it's starting to look really normal, like a normal distribution. And that's what we'll see. And so the bigger the degrees of freedom, the more normal it looks. But when we have a small degrees of freedom, like degrees of freedom 9, it's not going to look super normal. Here, we're looking at a one-tailed test because we said that the sheriff was going to improve these response times. There were going to be shorter response times. So we're going to do a one-tailed test low with our degrees of freedom 9. Our cutoff will be negative 1.833. So we want to put that cutoff, that one-tailed low test. Our cutoff is, again, that negative 1.833. If, again, you're not given an alpha value, if I don't say use this alpha value, use this as your probability, then you can go ahead and just assume it is 0.05 because that is our convention. If for some reason you have a crazy number someplace in a different class that isn't on your table, you'll just use that lower value from that table. So if you had, say, a 20 and a 30, and you've got 25 as your degrees of freedom, then you would pick the 20 as that lower value. But again, we're not going to do that in this class. So that is just to kind of think ahead. So let's put that t value on our distribution, our cutoff value. We have a 5% chance of making a type 1 error, and there's a 5% chance that the score will fall in this really extreme part of the distribution. Step 4 is where we're calculating that test statistic. We're going to take our mean of our sample minus our mean of our population and divide it by our estimated standard error. So 28 minus 30 divided by 1.17, that's -2 divided by 1.17. We get a t-statistic of -1.7. We're going to want to put that value on our t-distribution. So here are our cutoff values already. Put that value on our t-distribution, -1.17. And again, this step is really important because it can help us make those decisions in step 6, whether we're going to reject the null or not. And as you can see here, that sample is not in that critical region. It's outside of that. So we are going to fail to reject the null. Our results are inconclusive. Later on, we're going to get to a APA-style reporting result. You are not required to do that at this point, but I just want to start introducing you to what that looks like. A one-tailed t-test was inconclusive. T9 is equal to -1.7 non-significant. The new sheriff did not reduce response times. That could also look like a one-tailed t-test was inconclusive. T9 is equal to -1.7. P is greater than 0.05 because it was not in that critical region, right? The new sheriff did not reduce response times. Again, we're not to those APA-style responses yet, but we will get there. So I just want to start introducing those. As we discussed, just saying reject or fail to reject is a binary decision, and it tells us about statistical significance, but it doesn't tell us anything about practical significance. And that's where those measures of effect size are really important. Those measures of effect size start to get us to this information about practical significance in addition to statistical significance. So we did not have statistical significance in our example just now, and we don't always need to do a measure of effect size if we fail to reject the null, but it can be very, very important because, again, it's giving us this information about practical significance that we wouldn't ordinarily have. If you fail to reject the null, if you reject the null and you find that there is likely an effect, then we always have to do a measure of effect size because we want to know what that effect is. But again, it's always okay to do a measure of effect size whether you fail to reject the null or reject the null. If you reject the null, you always do a measure of effect size. Here at t-test, we have two different kinds of measures of effect size. Either one is fine unless I specify which one I want you to do. In this situation, we don't have everything we need for our estimated Cohen's d. We have the mean of the sample and we have the mean of the population, but we don't have the standard deviation of the sample. We only calculated the sample the sample variance. So here, that's a pretty easy pivot, right? We have that sample variance that we already calculated at 13.78. We're just going to need to take the square root of that to get that standard deviation. But you could see how it might be easier to do that R squared effect size, that a variability accounted for, how much is explained by the effect size, because we have all of that information. So for this Cohen's d, we now have everything we need. 28 minus 30 divided by 3.71. That will give us a measure of effect size of 0.54, which is a moderate effect. So again, we failed to reject the null, but we're still finding a moderate effect. And it could be because the new sheriff is so new and we only have 10 subjects in our sample. Again, that's not a very big sample. And when we have bigger samples, it's easier to reject the null because we have more extreme cutoff values on a t-distribution. Also, it's easier to find effects that are there. We have more power. And so even though we have a moderate effect here, we failed to reject the null, likely because of our effect size. Could be other things, but likely our effect size here. When we look at our squared, the variability accounted for, we are going to see that we take those t-values that we calculated, that was negative 1.7. We're just going to square that value both on the numerator and the denominator. Then we're going to add degrees of freedom at the bottom. So we have 2.89 divided by 2.89 plus 9. That will be 2.89 divided by 11.89. This will give us a effect size of 0.24. This is going to be 24% essentially of the variability is accounted for by the effect. So again, we're still having a kind of a moderate effect here, and this is giving us information about practical significance that our statistical significance didn't give us. The last piece of this that we wanted to talk about was constructing a confidence interval. A confidence interval is kind of like the flip side of the coin from doing null hypothesis significance testing. In significance testing, we're saying, okay, there's this 5% chance, this really extreme score. What's that going to be? Here we're saying, okay, I'm not interested in the extreme scores. I'm going to use this to estimate what the population mean is likely. And it's likely in this range somewhere. I'm not exactly sure where it is, but it's somewhere in here based on this sample, based on this information I have from this sample, and the likelihood that the score is in here on this distribution of sample means. So this formula, again, I failed to put on your formula sheet. So if you just write at the bottom of your formula sheet, confidence interval, copy this formula down, then you will have it on your formula sheet as well. This really is the same as our T formula for our single sample T statistic. It's just been algebraically rearranged so that we have it as a confidence interval. But again, writing that down can be very helpful. So how we would do that for our sheriff example, we have our mean, we have our estimated standard error of the distribution of means, and we know that we're interested in looking at this at 95%. Again, 95 and 99 are our typicals because they are that flip side of that coin from 0.05 and 0.01, that 5% or 1% chance. So we'll use our t distribution values. Notice that this is different than the cutoff we used, right? So the cutoff we used, we were using it at a one-tailed test. Confidence intervals can't be a one-tailed test because they're an interval. And so we're going to see that we're always going to use two-tailed tests here. So for degrees of freedom 9, our alpha at 0.05, which would be that counterpoint to that 95%, we get 2.262. We're going to solve that rearranged equation. So we're going to put that plus or minus 2.262 into our equation. We're going to put in our sample value of 28, or sample mean of 28, and our estimated standard error of 1.17. This is then 28 plus 2.65 and 28 minus 2.65. And so then we get this interval around our sample mean about where the population is likely, the population mean likely occurs. And so I can say that I'm 95% confident that the mean of the population falls within this interval, 25.35 to 30.65. If you think about what the sheriff was saying, I'm going to reduce response times, and I'm going to be better than the old sheriff, right? I'm going to have faster response times. The old sheriff's response times was 30. So while 30 is still contained in here, so we don't have really great evidence that they have improved, it might really be an improvement because we do see most of this interval is below. Again, this is why we're failing to reject the null, is because the comparison population that we're comparing it to, that mean does fall within this interval. But it could be that, again, the sheriff has made some improvements. And again, what this 95% confident is telling us is that somewhere between these two values in the middle is where that population mean is. We just don't know exactly where it is. But we're 95% confident it's somewhere between 28.35 and 30.65. So this ends our, wait, what am I supposed to be doing? our quick tutorial. Again, remember these are meant as supplements after class. So as a, wait, what did she say? What are we supposed to do? I forgot. I need a quick refresher. That's what this is. I hope these were helpful. Thanks.